Hello, student. How are you? I hope all of you are well and doing good. So, let's start today's session. That is your lecture number 8. Last time there was some technical error, so that's why we are going to start again. Today's topic is non-traditional machining method, as you can see. Now, before starting this topic, let me tell you we are going to cover this topic. We are going to cover ECM, that is electrochemical machining. Along with that, we are going to cover electrochemical grinding. Right, my dear, before starting these topic, this chapter, let me discuss you some basics. Right, let me discuss you some basics. The basic is why we need unconventional process. Right, why we need unconventional process. So let me write down here why we need unconventional process. Why we need unconventional unconventional process. Right, why we need unconventional process? Do you have any idea? Do you have any idea why we need the unconventional process? My dear, we need the unconventional process because some of the reason. Number one, new material which are coming, in this manufacturing process, they have a high strength and hardness. So let me write down new material. First of all, new material, right? New material which are coming, having high strength, having having high strength, right? High strength having high strength, right? And hardness, and hardness, and hardness, and hardness, right? Whatever the new material are coming, having a high strength and hardness, my dear, such as pneumonic alloy and alloy with alloying element such as tungsten, molybdenum, or columbium are difficult to machine by the traditional machining, right? New material which are having a high strength and hardness, basically they are difficult to machine by the traditional method. Okay, difficult to machine, my dear, difficult to machine, right? Difficult to machine by the traditional method, by the traditional method, by the traditional method, right? By the traditional method. So that's why we required some unconventional process, right? Untraditional process, unconventional process like ECM, electrochemical machining, right? And other processes, right? Along with that, my dear, along with that, try to understand by conventional machining, by traditional method machining, MRR gets reduced. MRR reduces with the increase in the work hardness and with the increase in work material hardness. Along with that, if you want to produce a complex shape, you are not able to produce a complex shape on a harder material by using conventional process or traditional process. That's why we need a conventional processes. That's why we need a conventional processes. Are you getting my point? Are you getting my point? Now now my dear, in conventional processes, let me start a very important topic of the conventional processes, that is ECM, right? That is ECM. What is the full form of ECM? Electrochemical machining, my dear. Electrochemical machining. Let me write down. It is what? Electrochemical machining, right? Electrochemical machining. This is the full form of your ECM, electrochemical. Are you getting my point? Now, electrochemical machining. Let me explain you what we do in electrochemical machining. My dear, there will be a container, right? There will be a container. Let me draw on the next page. So try to understand on a single figure. I will explain each and every concept. I will try to explain each and every concept, right? I will try to explain each and every concept. This is, see, this is a container, and this container, in this container, there will be a electrolyte, right? There will be a electrolyte. Now, so before that, just a minute, I have to change the color. Let the electrolyte should be in blue, right? The electrolyte must be in what? Must be in blue. This is the electrolyte. Now, in that electrolyte, there will be a electrode. This is a electrode, and this is the workpiece. And below the workpiece, there will be a work table. This is the work table, my dear. This is the work table, right? This is the work table. See, now here you can see this is the work table, my dear. See, this is the work table. This is the work table. This is the work table, right? And this is your workpiece. My dear, this workpiece, this is what? This is a workpiece. Here, this workpiece should be positive. The workpiece should be positive, and the tool, this is the tool or electrode, right? This is your what? This is the tool, my dear, right? This is the tool. See, this is tool, and this tool will be negative, that is cathode. So the workpiece is made the anode, which is placed in the closed proximity to an electrode, which is tool, or that is what? That is cathode. That is cathode. And a high amperage direct current is passed. And a high amperage direct current is passed between them through an electrolyte. This is what? This is the electrolyte, my dear, right? This is what? This is the electrolyte, right? This is electrolyte. Now this electrolyte, if the workpiece, my dear, let's say this is my workpiece, right? This is workpiece, right? If the workpiece, let's say if the workpiece is what? Let's say here, our workpiece. If the workpiece is iron base, right? Is iron base. Always remember, if the workpiece, hello everyone, if the workpiece is the iron base, my dear, in that case, your electrolyte, your electrolyte should be salt water. Should be salt water. That is what? NaCl.H2O. NaCl.H2O. This electrolyte is a weak electrolyte, right? This electrolyte is a weak electrolyte, and that electrolyte is flowing in between the tool and workpiece. Let me take a copy of this figure. Yes. So my dear, here you can see the electrolyte is flowing. Now, what is going to be happen? What is going to be happen, my dear? Here, when the high amperage current passes, when the high amperage current passes, metal from the workpiece side will be removed by anodic dissolution, right? Metal from the workpiece side. Here, metal from the workpiece side, metal from the workpiece side, metal from the workpiece side. See here, this is your metal, right? Metal that is from workpiece. Metal is removed by anodic dissolution. Anodic anodic dissolution, my dear. Anodic dissolution. Are you getting my point? Anodic dissolution, right? Anodic dissolution. So metal is get removed by anodic dissolution and is carried away in the form of hydroxide. What? Are you getting my meaning? Suppose that this workpiece is of iron base. Now, what is going to be happen, my dear? Let me explain you. Let me explain you. Suppose that this is your workpiece, right? And this workpiece is your iron base. Now, what is going to be happen? From that workpiece, the iron get removed in the form of atomic level, that is Fe plus 2, right? That is Fe plus 2. Now that iron get react with the electrolyte, right? That iron is going to react with electrolyte, that is Na plus Cl minus Cl minus plus H, okay, H plus plus OH minus. So this electrolyte get dissociated in this form, right? That electrolyte get dissociated in this form, as you can see, right? The electrolyte, that weak electrolyte get dissociated in this form, and Fe plus 2 react with OH minus, and it will produce, my dear. Let me write down. This is Fe plus 2 plus, okay, here I told you this is a salt water, so the major concentration of the iron is what? H plus and OH minus. Am I clear or not? The major ions which are present in the tank is what? H plus and OH minus, because it is what? It is the salt water. So here Fe plus 2 plus H plus plus OH minus is going to produce what? Iron hydroxide, FeOH2, right? Plus, along with that, hydrogen gas will produce it, right? So I told you, metal is removed by anodic dissolution and is carried away in the form of, okay, and is carried away and is carried away, okay, carried away in the form of, carried away, okay, in the form of, my dear, in the form of, carried away in the form of, in the form of, and is carried away in the form of, carried away in the form of a hydroxide, of a hydroxide, hydroxide, of a hydroxide. Is that point is clear? Yes or no? Is that point is clear? Now, my dear, when this iron hydroxide get produced, right, then what happened? It get collected, it get collected in between the gap, it get collected in between the gap, right? That iron hydroxide get collected in between the gap. So overall process is going to be what? Affected. So overall process is going to be what? Affected, my dear. So what is going to be happen? The electrolyte will flow in the gap, the electrolyte will flow in the gap, and it will remove the iron hydroxide. That iron hydroxide will collect at the bottom of the tank, and it will drain out, okay, and it will clean. That iron hydroxide will be recycled. Again we are going to what? Recycle, my dear. Again we are going to what? Recycle. Okay, we are going to what? Recycle. So when we are going to recycle, the the fresh, the recycled electrolyte, this is a filter system, will send to in a container, will send to in a container, right? Will send to in a container, and that recycled electrolyte, okay, again send into the container. Are you getting my point? So this is what overall you can say, it is a filter system. It is a filter system. That filter system basically remove that iron hydroxide. That filter system remove the iron hydroxide from the okay, from the electrolyte, and a fresh electrolyte again recycle with the help of pump. This is a pump, my dear. This is what? This is pump, right? This is pump. That iron hydroxide get recycled, okay, and it will sent into the container, my dear. Are you getting my point? Are you getting? Is that point is clear? So this process will go on repeatedly, okay, until the machining get finished, right? So there will be a gap, my dear student. There will be a gap in between the in between the in between the tool and electrolyte. That gap is known as Y. That is inter-electrode gap, right? Here Y is known as inter-electrode gap. Inter-electrode Inter-electrode gap. Are you getting my point? Now this inter-electrode gap, the value of this inter-electrode gap is not so much, right? The value of that inter-electrode gap is not so much, my dear, right? The value of the inter-electrode gap will vary from zero point 0.1 to 0.25 mm, right? So let me write down here. The value is going to vary, right? Here the value of Y get vary, okay? The value of Y vary from 0.1 to 0.1 mm to 0.25 mm. Yes or no? Yes or no? Is that point is clear? Right. Now, please remember one thing. When you are doing the machining, the gap height is going to increases. Why? Because material get dissolved from the workpiece side. So the gap is going to be increases. So whatever be the value of the Y throughout the machining process, the Y should constant, right? Throughout the machining process, Y should be constant, right? It should not change during the process. It should not change during the machining process. So that's why we provide a feed. That's why we provide a feed to the electrode, right? That's why we provide a feed to the electrode. That feed, basically you are not able to maintain the Y which will lie in the range which will lie in the range 0.1 to 0.25. You cannot maintain this range manually. So that's why on the axis of the tool, my dear, we provide a servo motor. There will be a servo motor. There will be a servo motor. That servo motor basically provide the feed in such a manner so that the gap is maintained throughout the machining. Am I clear? I hope this point is crystal clear. I hope there is a no doubt in this point, my dear. As you know, the Y is very small. So the overall resistance, right? So the overall resistance in between the gap, this is what? This is the Y, as you can see. This is the Y, as you can see, right? So this is the Y. Here the value of Y is very small. So the supply voltage, the resistance is very small. The resistance is very small, my dear, right? The resistance is very small. Okay, the resistance is very small. See here, the resistance is very small, right? Here Y is small, so the resistance very small, right? Resistance very small, so that's why the supply voltage supply voltage is going to be 2 to 35 volt. 2 to 35 volt, right? Supply voltage, I mean, this is not exact. The value of voltage will be vary, right? 2 to 35 volt DC. DC, volt direct, okay, DC. And the current range, and the current will be lie in the range of 500 to 40,000. 500 to 40,000 ampere. 500 to 40,000 ampere. Okay, that is a value of what? That is a value of current, right? And whatever whatever we supply the filter electrolyte with the help of pump, the pressure of the pump the pressure ranging from zero point 0.7 to 3 megapaskal. Right, you have seen that with we are filtering the electrolyte. You have seen that we are filtering the electrolyte. This is a filter system, right? This is a container, right? So here you have seen that, here you have seen that, here you have seen that, please see, here you have seen that, see, this is a filter system. Now after filtering, we are going to send that thing into into the next container, and that filtered thing will be supplied again into a again into a container with the help of pump, with the help of pump. You know the pressure of the pump? Do you know the pressure of the pump? Can anybody tell me the pressure of the pump? The electrolyte needs to be pumped through this gap. The electrolyte needs to be pumped through this gap at a high pressure ranging from 0.7 to 3 megapascal. 0.7 to 3 megapascal. So this is the pressure range, my dear. This is the pressure range, right? This introduce a large amount of load. This introduce a large amount of load on the machine because of the large working area involved. Because of the large working area involved, hence the machine structure will have to be made rigid. Hence the machine structure will have to be made rigid to withstand such forces, right? I hope you understand this point in a very crystal clear manner. Okay, in a very crystal clear manner. Now let me discuss the formula, right? Let me discuss the basic formula. Now you are removing the material. Okay, you are removing the material in the form of atomic form. So what will be, so how much material you are going to remove in this process? So how much material you are going to remove in this process, my dear? The material which you are going to remove, right? Formula, MRR formula, material remove formula, material removed formula, right? Material removed formula, right? So the removed, the formula will be what? M is the mass of the material which is going to remove from the workpiece, equal to current which is going to supply into time into E, that is a gram equivalent weight, that is atomic weight, divided by valency, divide by F, that is Faraday constant, that will become in gram. Let me write down what is here M. M is what? Weight of the material which is removed. Weight, that will be in gram of material, of material, weight of material which is going to be what? Removed. I is what? Current, current, right? Which will be in ampere, which you supply. E is what? Gram equivalent weight. E is gram equivalent weight, gram equivalent weight of the material, of the material, of the material, of the material. Basically, it is nothing that it is atomic weight divide by valency, divide by valency. That is what? That is a E, right? And F is what? F is a Faraday constant. F is a constant of proportional. Okay, constant of proportionality, constant of proportionality. Okay, constant of proportion, proportionality, constant of proportionality, and its value is basically it's a Faraday, right? Basically, it is what? It is a Faraday, right? It is a Faraday, and its value is 96500 coulombs, right? Coulombs, coulombs. Okay, its value is 96500 coulombs, right? So please remember this one. This is a very important and basic formula, my dear. It's a very important and basic formula. Now, suppose that if you are want material removal rate, okay, then it is what m dot, that is what m by t. So this formula become what? Your I E divided by Faraday, that will be in gram per second. Suppose that if you know the density of the material, right? Rho is the density. Let's say I'm going to write here rho density, density, right? Density of material, right? That will be in, let's say, gram per centimeter cube. Now, which density is that? The density of the workpiece, which you are going to be what? Machine, right? Which you are going to be what? Machine. So, my dear, the material removal rate in volume will be what? I E divided by F into rho centimeter cube per second. So, please remember this formula. Please remember this formula. Also, my dear, you understood that the electrode is moving right in a downward direction. The electrode is moving in a downward direction. The electrode is moving in a downward direction with a feed what? With a feed of F, right? And having a cross sectional area A. Okay, F is what? Feed of the feed of the electrode. Feed of the electrode, right? It will be generally in mm per minute. If you generally gate will ask the standard unit of feet in mm per minute. A is the cross sectional area, cross sectional area of electrode, cross sectional area of electrode. So material removal rate is cross sectional area into feet, right? Cross sectional area into feet. So it is also centimeter cube per second. My dear, you can also write that that A into feet of the electrode equal to I E divided by Faraday constant, okay, into rho. So the feed of the electrode, you can find out that I E divided by F into rho, right? That will be a feed which comes in mm per second. You can convert in mm per minute. That is a standard unit. Right. So there is no need to remember this formula, remember this thing and this thing. You can automatically get the feed, okay, if it is required, right? If it is required, if it is required, right? My dear, this is basically the formula. This formula is basically for pure alloy. Try to understand. This formula is for what? Pure alloy, right? This formula is basically for pure alloy. Suppose that if you are machining, that this formula is for what? Pure metal. MRR for material removal for material. Okay, for material for pure metal. For pure metal. Right? Pure metal. Suppose that if you are machining an alloy, then what you will do? If you are machining an alloy, then what you will do, my dear, in that case, for alloy, right? For alloy, for alloy, right? For alloy. Are you getting my point? So, my dear, suppose that this is your workpiece, and you know that alloy is made up of okay more than two or more than two material. Let's say I'm going to take what? Three metal. That is what? That is your metal one, right? That is your metal one. Okay. that is your metal 1. Let's say metal 1, let's say metal 2, let's say metal 3. The overall composition of alloy is what? 100%. The overall composition of an alloy is what? 100%. Now, let's say metal 1 will be 60%. Let's say I'm assuming, right? Metal 2 is 10%. Let's say metal 3 is 20%, right? Metal 3 is at 20%. So, my dear, it has a 3 metal. Try to understand what I want to say. It has a 3, right? It has a 3 metal, right? It has a 3 metal. Try to understand what I want to say. It has a 3, right? Atomic, every metal has atomic weight, valency, right? E, density, right? So try to understand. Every metal has its their own atomic weight. Atomic weight, VIGST. Let's say atomic weight 80 W. Atomic weight is going to be represented by 80 W. So metal 1 has an atomic weight what? 80 W1. Metal 2 has an atomic weight 80 W2. Metal 3 has an atomic weight that is 80 W3. Every metal has its own valency, right? Valency. Every metal has its own valency. Let's say valency 1, let's say valency 2, and let's say valency 3. Gram weight, gram equivalent weight. Okay, gram equivalent weight, as you have seen that gram equivalent weight, gram gram equivalent equivalent weight, okay, gram equivalent weight, that is E, is what? You know that gram equivalent weight E, basically it is 80 W divided by valency. So it has a E1, it has a E2, and it has a E3. That is what? It's the atomic weight divided by what? Divided by valency, my dear, right? And density, density of each metal. Density is represented by rho 1, rho 2, rho 3. Now the question is, in material removal rate formula, which thing you can put? Very simple. Let me write down the formula. My dear, the simple formula which you have seen, the material removed, that is I T E divided by Faraday constant. My dear, current is constant. Current is not going to be changed. E is not depend on the material type. Okay, E. So here E will be what? Equivalent. I mean equivalent of the 3. F is a constant. This is your material remove. If you are talking about m dot, so it will be I E equivalent divided by F, that will be in gram per second. If you are talking about volume per unit time, okay, material removal rate in volume per unit time, that I, okay, E equivalent divided by Faraday into rho equivalent, that will be in centimeter cube per second. Now rho is the equivalent, okay, of the 3 metal. Now the question is, sir, how can we find the rho equivalent and E equivalent? Very simple, my dear. Now rho equivalent, let's see the calculation of rho equivalent. The overall composition of alloy is what, my dear? 100%, right? Divide by rho equivalent, right? Divide by rho equivalent equal to summation I, number of metal, 1 to capital N, right? Capital N, number of metal, okay, into summation. Summation, basically we are summation, we are going to summationing of all the material from 1 to N, okay. Percentage of ith metal divide by density of the ith metal. Are you getting my point? Let's expand this formula according to this, my dear. Percentage of metal 1 divided by density of metal 1 plus percentage of metal 2 divided by density of metal 2, right? Plus percentage of metal 3 divided by density of metal 3, right? So 100 divided by rho equivalent equal to percentage of metal 1, that is 60 divided by rho 1. Percentage of metal 2, that is 10 divided by rho 2. Percentage of metal 3 is 20 divided by rho 3. You will get you will get the value of E equivalent. You will get the value of what? Value of E equivalent. Are you getting my point? Now, similarly, you can find the E equivalent, right? Now, the question is, sir, how can we get the E in a similar fashion? My dear, in a similar fashion, you will get the value of E equivalent. How? See, 100 divided by E equivalent equal to summation I1 to metal n percentage of metal ith metal divide by E gram equivalent weight of ith metal. Now expand this. If you are going to expand this, then percentage of metal 1 divide by E1, percentage of metal 2 divide by E2 plus percentage of metal 3 divide by E3. Now if you are going to put the value here, percentage of metal 1 is what? 60 divide by E1 plus percentage of metal 1, that is what? 10 divided by E2, percentage of metal 3, that is what? 20 divided by E3, right? Now from this equation you will get the E equivalent value. Now once you know the value of equivalent and row equivalent, right? Equivalent, sorry, I have written that equivalent. Now you will get the value of what? Row equivalent. Now once you get the value of row equivalent and E equivalent, put the value in this formula, you will get your desired MRR. You will get your desired, okay, MRR. I hope you understand this point. Okay, I hope you understand this point. One more thing which I want to discuss with you, one more thing which I want to discuss with you, that is what? That is a over voltage or a current density, right? Or a current density concept, right? Current density concept. Just a minute. Let me discuss with you current density concept. Yes, current density concept and over voltage. Current density voltage and over voltage. Current density, that is represented by J, and over voltage. Over voltage, right? And over voltage, my dear. Now here, please see. Now here, suppose that this is your suppose that this is your electrode, right? This is your electrode. Suppose that this is your electrode. See, this is the electrode. See here. See, suppose that the cross-sectional area of the electrode, the diameter of the electrode is d, right? And below that there is a workpiece. Below that there is a workpiece, and the electrolyte which is present here, the electrolyte which is present here, okay, which is flowing in between the gap, is this. Now the current is flowing through that electrolyte, right? And what is the gap of this electrolyte? Basically the gap of this electrolyte is, the gap of this electrolyte basically is y, in which the current is flowing. Now this electrolyte will look like, this electrolyte will be look like as what? As a current carrying wire, my dear. As a current carrying wire, right? This electrolyte will be look like as a current carrying wire. Yeah, this electrolyte will be look like as a current carrying wire, right? This electrolyte will be look like as a current carrying wire. See, okay, are you getting my point? So here please see, this is the electrolyte through which through which through which the current is flowing. Now whatever be the cross sectional area of the electrode, A is what? A is the cross sectional area of electrode, okay, electrode. Through the same cross sectional area, through the same cross sectional area, current is flowing. right? The gap height is what? Y. Basically this gap will act as a current carrying wire, right? This gap act as a current carrying wire. Are you getting my point? If this is a current carrying wire, if this gap will act as a current carrying wire, my dear, A is what? A is the cross sectional, right? Cross sectional, and it act as a current carrying wire. Now my dear, it has a height y. A is a cross sectional area. Suppose that it's a specific resistivity, right? Suppose that it's a resistivity specific resistivity specific resistivity resistivity, okay, of electrolyte is what? Let's say S ohm centi, right? Ohm centimeter. Now then the resistance of this gap, resistance of interelectrode gap, resistance of interelectrode gap, resistance of resistance of interelectrode gap, interelectrode gap is what? Let's say Re, right? Re, that is equal to what? A specific resistivity of the electrolyte into length of the wire divided by A, divide by A. Am I right? So this is the equation number one, let's say, right? And here you have applied the potential difference, that is what? That is a negative and that is a positive, and there is a potential difference of what? There is a potential difference, okay, there is a potential difference, right? There will be a potential difference, there will be a potential difference, there will be a potential difference, okay, which is equal to V, right? And there will be a drop voltage that is equal to what? V naught. Now if you apply Ohm's law, Kirchhoff's law in the circuit, then what you write? You will write that V minus V naught equal to I into Re. Here this will act as a resistance, right? Now this is what? This is the equation number two, my dear. This is what? This is equation number two. Now if you are going to compare this, then V minus V naught I Re is what? S L by A. My dear, please see this thing. I divide by A, right? So I divide by A, that is a current density, into S, that is S. V minus delta V, L comes here. Basically, L is nothing, that is a gap of interelectrode gap. So here you can see that this is the relation, right? Generally the drop voltage is very small, generally it is very small, right? It is very small. If it is not given, if it is not given, then you can neglect this. If it is not given, then you can neglect this one. Okay, so I hope you understand this thing. Now let's move. Okay, now please see some numerical. Now once you solve the numerical, you will get the better touch, okay, you will get the better understanding of the concept, right? So using the electrochemical machining, removal 5 centimeter cube per minute from an iron workpiece, what current is required? So what is the required value of the current, my dear? Here MRR is given. Here MRR, here material removal rate, here material removal rate is 5 centimeter cube per minute, right? uh Atomic weight is 56, density is 77.8 gram per centimeter cube, valency, right? So there is no need to write here, my dear. You know that material removal rate equal to what? I into E, divided by F into rho centimeter cube per second. Am I right or not? Am I right or not? Yes. Clear? Now, my dear, once you apply this formula, right? Once you apply this formula, the MRR is given, that is 5 centimeter cube. So 5 divided by 60, then it will be centimeter cube per minute. I, we have to find out E, that is a gram equivalent weight. It is what? It is 56 divided by 2 valency divided by Faraday constant 96500. Always remember 7.8, 7.8. Now it will become centimeter cube per second. Now you will get the value of what? You will get the value of what? Current, right? You will get the value of what? With the value of current. So what will be the value of current here? So 5 divided by 60 into 96500 into 7.8. Answer divided by 56 divided by 2. So here the value of I will be 2240.17. Right. This is the value of the current. This is the value of the current. Is that clear? I hope the point is crystal clear. Now let's move to the next question. In an electrochemical machining, operating a square hole of a dimension 5 mm cross 5 mm is drilled in a block of a copper. The current used here, the used current is 5000 ampere. Atomic weight of copper is 63. Valency of dissolution is 1. Faraday constant is 96500 coulomb. The material removal rate you have to find out in gram per second. So my dear, material removal rate in gram per second. Okay, material removal rate in gram per second. So what was the formula? Remember what was the formula? The formula is very simple. That is your I into E divide by Faraday constant gram per, right? So I is given 5000, 5000. E, that is 6 divided by 1. Faraday constant 96500. Here coulombs, so it will be in gram per, right? It is what? 5000. So my dear, 5000 into 60, right? Answer divided by 96500. So here the material removal rate will be 3.264 gram per second. 3.26. Option B is the answer, right? Option B is the answer. Now the next question. Please see the next question. A researcher conduct electrochemical machining on a binary alloy. There is a binary alloy, right? There is a binary alloy. This is the alloy. Binary means it's made up of two materials, and that binary alloy has a density of what? Has a density of 6000 kg, 6000 kg per meter cube, right? Per meter cube. Atomic weight, okay. It is made up of iron. It is made up of iron. Let's say it is a metal 1 and metal P. Let's say it is metal 2. Okay. Iron has an atomic weight of what? 24. And okay, here's the information that iron has atomic weight of 24 and valency 4. But a constant which you have to use, that is 96500 per mole. Volumetric material removal rate of the alloy is 50 mm cube per second, right? At a current of 2000 ampere, the percentage of the metal B, you have to find out the percentage of metal P. Now how can we solve this question? Please see, right? Please see how can we solve this question. Look, let's say we know that overall composition is what? 100%, right? Let's assume that the percentage of metal is X. Then the percentage of iron is what? 100 minus, right? 100 minus X%. Now here density is given, right? Density is given. So material equal rate equal to 50, right? mm cube per second. My dear, you can write that 50 to 10 to the power minus 3 centimeter cube per second, right? Equal to what? I divided by Faraday into what? Faraday into density, right? So 50 into 10 to the power minus 3 I is given, that is what? 2000 ampere. 1000 ampere into E, that is what? Equivalent. Basically here we use what? Equivalent, right? Here we use what? E equivalent. And E equivalent right here, E equivalent, right, divide by Faraday constant 500 into density, that is 6 kg per meter cube na, so it will be gram per centimeter cube, right? So 50 into 10 to the power minus 3 into 96500 into 6, answer divided by 2000. So here E equivalent will be, here will be 14.475, right, gram per mole, right? Now we know that, my dear student, that 100 divided by E equivalent equal to percentage of metal 1, right, divide by gram equivalent of metal 1, percentage of metal 2, gram equivalent of metal 2. So 100 divided by 14.475, 14.475 equal to percentage of metal P, that is 2, let's say X. So X divided by, okay, P. Now the atomic weight of P is what? Atomic weight of the P is 24 and valency is 4. So atomic weight 24 by 4. So it is what? 24 by 4 plus X2, let's say it is iron. Okay. If, okay, I'm going to write X1 is what? Basically 1 is a metal 1 na? So 1 is a metal 1. Iron. Iron has atomic weight of what? Iron has atomic weight of what? 56 and valency is 2. So here, here 100 minus X, percentage of iron, E 56 divided by 2. 56 divided by 2, right? 56 divided by 2 plus X divided by 24 divided by 24 divided by 4, right? Divide by. Now here we can solve. So we will get the approximated value, that is what? 20. This is the approximated value, 25%, right? So I hope you understand this concept in a very well manner. Okay, you understand this concept in a very well manner. Okay, so this is the thing. If you have any doubt regarding this point, you can ask me, right? You can ask me. Okay, you can ask me. Now I'm going to discuss the last point, that is the electrochemical grinding, basically, right? That is the electrochemical grinding. What is the electrochemical grinding? Yes. Electrochemical grinding, basically it is a theoretical portion, right? It is a theoretical portion. ECG, it is a nothing that electrochemical grinding, right? It's nothing electrochemical grinding. Let me write down electrochemical grinding. Chemical grinding. Electrochemical, right? Electrochemical grinding. My dear, instead of electrode, there will be a rotating wheel. Always remember, instead of electrode, there will be a rotating wheel. Okay, which will rotate over the workpiece. Which will rotate over the workpiece. Here the electrode is, okay, this rotating wheel is made up of what? Cathode. Basically, it is a cathode, right? It is a cathode, right? And here the workpiece is what? Here the workpiece is, again, the setup was submerged in, again, the setup, basically, we are going to supply a dielectric medium. We are going to supply a dielectric medium. Oh, sorry. We are going to supply a electrolyte. This is the electrolyte which we supply, right? This is the electrolyte which we supply. Now, my dear, in this electrode, there will be a, what? There will be a grit, which are what? Which are non-conductive. These grit are what? Non-conductive, and they are attached to the wheel with the help of what? With the help of some metallic bond. So this is a grit, my dear. Here you can see this is a grit, right? This is the grit. 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 Right? So I hope you are under. Are you? I hope you are getting this point. This is the grit. This is the grit. This is the grit. Grit. This is the grit. 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 So these are the non-conductive. These are the grit. Okay. These are the grit which are non-conductive. Abrasive particle, non-conductive, abrasive, non-conductive, non-conductive, abrasive particle, abrasive particle. Okay. Which are attached to the wheel, which are attached to the wheel with the metallic bond, which are attached to the wheel with the metallic bond. See, this is what? This is the metallic bond. Metallic bond. This is what? This is the metallic bond. Metallic bond. Metallic bond. Now, the current will pass through the metallic bond and electrolyte in the workpiece. Right. Now, what is going to be happen in the presence of electrolyte? Right. In the presence of electrolyte, what is going to be happen? Let me explain you. The surface, right? The surface metal, the surface of the workpiece is changed to what? Is changed to metal. The surface metal is changed to metal oxide, my dear. Here the surface, right, the surface metal is changed to the surface metal, the surface metal changed to the surface metal changed to metal, changed to a metal oxide, changed to a metal oxide, right? Changed to a metal oxide. Now, once the surface is changed to a metal oxide, then what is going to be happen? The abrasive particle will remove that metal oxide from the surface, which is ground away by the abrasive, which is ground away, ground away by the abrasive, by the abrasive. It is ground away by the abrasives, right? And this process will continue till the machining is not going to be completed. So as the oxide film is removed, new surface, new surface metal is oxidized and right. So as the right as the oxide film is removed, as the oxide film is removed, right, as the oxide film is removed, new surface metal is new surface metal is new surface metal is oxidized and removed, oxidized and removed, right? Oxidize and what? And it will remove, right? So similarly, electrochemical grinding is whatever the characteristic we have found in electrochemical machining. Now, same characteristic is present in electrochemical grinding. Low voltage, high current electrical process. Electrochemical grinding is electrochemical grinding is electrochemical grinding electrochemical grinding is what? Is a low voltage and high current, is a low voltage and and low voltage and okay, low voltage and high current electrical process, and high current and high current electrical process, electrical process, low process, okay, electrical process, right? Now you may be surprised, sir, why we use the abrasive particle here. The purpose of the abrasive is to increase the efficiency of the electrochemical grinding process and permit the continuance of the process. The purpose of the abrasive particle, the purpose of the purpose of, right, please try to understand what I'm writing here. Very important point. The purpose of the abrasive is to, the purpose of the abrasive is to, right, the purpose of the abrasive, okay, is to increase the efficiency of, increase the efficiency of, the efficiency of what, efficiency of, efficiency of electrochemical grinding, efficiency of, okay, efficiency of, efficiency of electrochemical grinding, efficiency of the electrochemical grinding process, right? So I hope you understand this process in very well manner. Thank you very much for watching this.